Hi there. So this is going to be a very quick lecture just to finish up what we did in class on deriving Snell's law using optimization. Okay, so we won't have so much time during the double period, so this video is just going to finish off what we started earlier. Okay, so we had the following situation here. Okay, we had our x-axis and the y-axis. We had some point A where the light was starting. We had some point B where the light was ending. And we said that it would follow this particular path, like this, where we have theta 1 and theta 2. Okay, so at the end, we also had L1 and L2 being the lengths of those individual paths. Okay, and at the end I said that the distance between A and B was fixed, and we could use that to eliminate one of the variables. Now, the class did seem a bit lost going through all of the trig, so we're going to go through a method that doesn't involve so much trig just until the end. Okay, so we're going to try this method out. Okay, but if you do want to go back and use the trig method just to try it out, please feel free to do so. Okay, so let's call this distance x, and we said that the full distance was a constant, so from A to B was a constant. If we call this x, in the lecture I called it x1, but let's just call it x here, then that means this distance will be d minus x if the full horizontal distance from A to B was a constant. So in the lecture I called it s. Here I'm just going to call it d, just so that we don't have too many variables in this lecture now. Okay, let's call this A, and let's call that B. Again, in the lecture I called that y1 and y2. Okay, I'm just going to give it different names so we don't confuse the different x's and the different y's and so on. Okay, so we had the total time t, we said was t1 plus t2, and we worked this out as L1 over V1 plus L2 over V2. Now this L1 and L2 we can write in terms of the angles, but again the class seemed very confused with the angles and the trig, so I'm going to write it in terms of x. Okay, maybe that would be a bit easier to work with. Okay, so we're going to have t is equal to L1. Okay, if we write that in terms of x and a, like we had before with the x1 and y1, this is going to be the square root of a squared plus x squared over v1 plus L2. We can work that out. That's going to be b squared plus d minus x squared. Okay, all over v2. Okay, so now we have this in terms of x. Okay, so this is a single variable function. Everything else is constant. We can differentiate with respect to x and set the result equal to 0. So let's find t prime. Okay, so I'll just do this quickly. You can work out the individual steps, but here we're going to end up with 1 over v1 times x over the square root of a squared plus x squared. Okay, so the 2 from the chain rule, that will cancel out the 2 from when we take the root down. Okay, so please, if you need to go through this step by step, please do that. And then we're going to have minus 1 over v1 e minus x over the square root of b squared plus d minus x squared. Again, I'm leaving some steps out. If you do need to go through it more slowly, please do that. Okay, and if you have any questions on it, again, please don't hesitate to email me. Okay, so this is going to be set equal to 0, again using our local minima and maxima rules. Okay, since this is equal to 0, we can take this negative term over to the other side. So we have 1 over v1, x over the square root of a squared plus x squared. This is equal to 1, this v2 here, that should be a v2, not a v1. So we have 1 over v2 d minus x over the square root of b squared plus d minus x squared. Okay, so now we can go back to using our trig formulae. Okay, so you can either work the whole way with trig, or you can just put in the trig at the end. Okay, so here we're going to include the trig again. So x over the square root of a squared plus x squared, we know what that is. The square root of a squared plus x squared, that was our L1. So this is going to be x over L1. And then we're going to have 1 over v2 d minus x over, again, the square root here. This was our L2. Now x over L1, if we go back to our diagram, let's just put in the line here. So here, this is our x, here's our L1. So in terms of theta 1, x over L1, that's going to be sine of theta 1. Okay, so I did go through that in the lecture. And then d minus x over L2, that's going to be sine of theta 2. So those two ratios we can replace with sine theta 1 and sine theta 2. Okay, please just go back to your lecture notes if you don't see that immediately. So here we have 1 over v1 sine theta 1 from the trig ratio, and then we have 1 over v2 sine theta 2, again from that trig ratio. Now we want to turn this into the Snell's law with the refractive indices. The way we can do that is multiply through by c, speed of light. So c over v1 sine theta 1 is equal to c over v2 sine theta 2. And then this ratio of the velocities, that's just the definition for the refractive indices.